Bismillahirrahmanirrahim. All structures are subjected to external loads and are supported at the supports. External loads are categorized as surface or contact forces and body forces. The body forces are applied from a distance and they act on the volume of the body and are therefore expressed in Newton per cubic meters or Newton per cubic millimeter, as the case may be. Now, gravitational and electromagnetic attraction or repulsion are examples of body forces. Body force is shown here, weight of the body. Now, body forces act on each particle of the body, but they are usually idealized as a single resultant force acting at the center of gravity of the body. Surface forces, on the other hand, are applied through contact with other bodies. And are always distributed. In that they are applied on a finite area of contact. That is why they are expressed in Newton per square meters or Newton per square millimeters. A familiar example of a contact load is a body submerged in a fluid. This contact force, for example, acts on this area A. So contact force as a rule is expressed in Newton per square meters or Newton per square millimeters. But there are two idealizations of contact force. The first one is linear distributed load idealization. This is where the distributed load is applied on a narrow strip of an area. Let's consider this narrow strip of an area on which this distributed load is being applied, so that the distribution is symmetric above the center line. The center line is the line shown in blue. In this case, the distribution is then expressed in Newton per meters. The resultant is equal to the area under the loading curve and acts through its centroid. Two examples of linear distributed load idealization are shown, with the magnitude of the resultant in each case, which is the area under the loading curve, as well as their line of action, which passes through the centroid. In one case, it is the midpoint, and in the other, 1/3 from one side and 2/3 of the way from the other side. Now, the second idealization of contact force is when the area of contact is very small as compared to the overall surface area and is not known exactly. For example, the force here actually acts on a finite area like all contact forces, but this area is very small as compared to the overall dimensions of the surface, and in addition, it is not known exactly. So in this case, it is taken as a concentrated force in newtons. Now let's talk about the supports and the reactions that they provide. As a result of the application of external forces, the supports supply reaction forces, which are also external. These forces are produced to keep the body in equilibrium. Reactions can be calculated by isolating the body from its surroundings. Notice that we have done precisely that, and this is called the free body diagram. recall that in the free body diagram, only forces acting on the body are shown. That is, the forces applied by the body to the supports are not shown. Because in rigid body statics, we deal with equilibrium problems. It is the equations of equilibrium that yield these reaction forces. Let's review the equations of equilibrium. In 2D problems, there are three scalar equations of equilibrium. That is, summation of forces in the x direction equal to 0, summation of forces in the y direction equal to 0, summation of moment about any point on or outside the body equal to 0. In 3D problems, there are 6 scalar equations. That can be used, but it is much more convenient to use the 2 vector equations. Namely, summation of force here and summation of moment any point. Now a few words on internal forces. Now, if the whole body is in equilibrium, then any part of it must also be in equilibrium. So we can pass an imaginary cutting plane arbitrarily through the body. Now, just as we employed the free body diagram for the whole body to calculate the external reaction forces, we can make a free body diagram of one portion of the body and apply the equations of equilibrium to calculate the resultant of the internal forces acting on the section. Now, this internal force resultant generally takes the form of a force and a couple moment that can be calculated at any arbitrary point O on the section. In 3D problems, this resultant force and the resultant couple moment will have at most 3 orthogonal components each along the x, y, and z axes. These are the x, y, and z axes. Now these components are called normal force. This is 1 in number, perpendicular to the section. Shear forces, Vy, Vx, 2 in number. They are in the plane of the section. Bending moments, Mx, My. These are also in the plane of the section. And a torsional moment, 1 in number, which is acting perpendicular to the plane of the section. Now these classifications are based according to their action on the body, whether it's push or pull, sliding, bending, or torsion. In 2D problems, there will be one bending moment couple about the out of plane axis, and at most two orthogonal components of resultant force N and V along the two in-plane axes, one normal and the other shear. Now let us take up two examples. We are required to determine the resultant of internal loading acting on a cross section passing through point A. Now, infinite number of planes could pass through point A. For example, this one, this one, and countless others. And no specific section has been specified. Let us use a section that is perpendicular to the longitudinal axis of the body. This is the longitudinal axis, and this is the perpendicular section. This is a usual practice. This practice served us well in rigid body statics as it will in mechanics of materials. Here we have cut the section accordingly. Let's start with specifying the coordinate axes. Now let's show the potential components. So this is the normal component. Let us show all of them in their positive senses so that if one of them turns out to be negative, that would mean that it actually acts in the opposite sense to what we had assumed. 2D case, so there is a normal force, a shear force, and a moment. We have three equations, summation of force in the x direction is 0. This means that there is no applied force in the x direction. Second equation, Fy is equal to 0. This gives us plus 1000 minus n is equal to 0, which means that n is equal to 1000 newtons. The third equation, summation of moment about any point is equal to 0. Let's take point A. Summation of moment about point A is equal to 0. This gives us m plus 1000 into 0.2, taking distance in meters, equal to 0. This means that m is equal to minus 200 Newton meters, which means that actually it is acting in the opposite sense that initially assumed. So what is happening actually is it is acting actually like this, and n is equal to 1000 newtons, and there is no shear force acting. Now let us take a 3D example. The signboard is facing a uniform wind load perpendicular to its surface. Intensity is 500 Newton per square meters. We are required to determine the resultant internal loading at a horizontal cross section. It will be a section 9 meters from the top. Will be this section. Here, horizontal has been specified, so we'll take that. But like in the last example, even if nothing was specified, we would have done the same. So we have marked the coordinate axes. Now we show the potential components on the cut section at O. As is our practice, let us show them in their positive senses. We have three moments. This is mx, my, these are the bending moments, and t, this is the twisting moment, all shown in their positive senses. And then we have three force components acting at point O of the cut section, which is point O, which is the centroid. These three forces, Vx, shear force, V by another shear force, and N is a normal force. Point O is taken at the origin 0, 0, 0. Now, the wind force F can be expressed as a vector. Let's do so. Magnitude first. Magnitude is 500 multiplied by the area of this board, which is 3 into 5, which turns out to be 7500 newtons, or in kilonewtons 7.5 kilonewtons. This is the magnitude, but if we express it in vector form, because this is a 3D problem, it helps to solve it using vector equations. We can write the same thing as 7.5 kilonewton I. This means it is in the x direction, and negative sign because it is acting, this force is acting in the negative x direction. Now this acts on the whole area, so its line of action must be on the centroid of this board, and that centroid happens to be on the intersection of the two diagonals, and it is obvious that this distance from the center of the pole is 0.5 meters. Now we are in a position to apply the vector equations of equilibrium. First, the force equation. First, there are the reaction forces. These are what we are interested in finding. It's V by J plus Vz K minus 7.5 I. Just calculated this here. Is equal to 0. This means that Vx is equal to 7.5 kilonewtons, Vy is equal to 0, and Vz. So we just have one reaction force at point O. Now let's take up the moment equation. Again, just one equation because we are dealing with vector equations. Mxi plus myj plus t k. Now there's only one force that is not passing through point O, and that force is the wind force. So we need only worry about the moment produced by this force in addition to the three couple moments and reaction. And that will be given by simple cross product ij k rx ry rz fx fy fz, and this must be 0, and here this is the position vector from O to any point on the line of application of the 7.5 kilonewton force. We can simply figure that out. Let's put that values yj plus t k plus ij k. Values here should be 0 minus 0.5. This minus 0.5 with this one. Minus because the vector goes in the negative y direction. Here we have in that direction we have 7.5. As far as the force is concerned, it is only in the negative x direction, so it is minus 7.5, 0, and 0. This must be equal to 0. Simplify it. We get mxi plus myj plus t k minus 56.25j minus 3.75 k is equal to 0. This implies that mx is equal to 0, my is equal to 56.25 kilonewton meter. Make sure you are consistent with your units. T is equal to 3.75 kilonewton meters. Now let's summarize our results that we have calculated for point O. This is the axis, this is the y axis, this is the z axis, and as far as the non-zero components are concerned, this one force component which is non-zero, and we have two couple moment components that are non-zero. Let's show the let's show the force first, which is 7.5 Newton in the positive x direction, 7.5 kilonewton. Then we have my, which is the moment about the y-axis, and it is positive, so again positive sense, 56.25 kilonewton meters. And finally, moment t, which is torsional moment, again in the positive direction, show here, in the positive sense.